energy in one direction, and they receive it back in one direction. Okay? They have to be pointed in the direction of interest. The directional antenna makes your signal sound stronger. The directional antenna makes the received signal sound louder. Okay? Now, you can also take and put more elements on a quad. And we go again. Here's a quad with a reflector. So the two-element quad is as strong as the 1, 2, 3 element Yankee. And it's cheaper to make. It's just wire. No, not too bad. Okay. Next thing we want to talk about is polarization. When the signal comes off of the radio, let me go back to my little. Well, I took my antenna off here, but let me just try to put it back on for a second. When the signal comes off of my radio, it goes into the antenna. Let me just get this here. Okay, when the signal comes out of here, it depends. The signal wants to just be like a wave coming off. Well, is the wave like this or is the wave like this? Well, if the antenna is physically horizontal to the ground, the wave comes off horizontal to the ground. If the antenna is physically vertical to the ground, the wave comes off vertically. So, vertical polarization. This is the electrical lines of force of radio waves are perpendicular to the Earth's surface. Okay, so that's off of here, off of here. These are vertically polarized. Horizontal polarization, electrical lines of force are parallel to the Earth's surface. Okay, like dipoles in that beam when I mount the beam. Okay, here's the problem. So you have best communications when the polarizations are the same for both the antennas. So if I'm talking to a repeater, the repeater's up on a hill. Guess what? It's a vertical antenna. Because it doesn't know in which direction you are, so it radiates in all 360 degrees. So when you're talking on a handheld, you hold the handheld vertical, because you want this polarization to match the repeater. If you start talking like this, you just change the polarization to horizontal. See, you can, depends on how the antenna is. Just because it's a handheld doesn't mean it's vertical. You have to hold it vertical, keep it vertically polarized to talk to the repeater, which is vertically polarized. Now, if you do this and you're close, sure, you'll talk to the repeater. But if you're in a bad signal condition, you want to keep it vertical. Okay? More about polarization. Okay, well, I think I just gave you this. Repeaters use vertically polarized antennas so they can receive and transmit all around 360 degrees. We use vertically polarized antenna, handhelds, or the mag mounts for best communications for the repeaters. Radios are using VHF and UHF. Now that's the line of sight frequencies that you have. And are not the same polarizations. The signal could be significantly weaker. Now, as I just told you, if you're holding your radio with the antenna horizontal and the repeater vertical, you could lose the signal. Okay. So you always keep your handheld antenna at the same vertical polarization. Let's see more about antenna stuff. Horizontal polarization is normally used for long distance weak signals. Okay, just memorize that. So if I want to do if I'm going long distances and the signals are weak, I would tend to use horizontal, but just memorize that answer. Also, when using directional antennas, like this would be a directional antenna, and I'm doing this to get to a repeater where buildings or obstructions are blocking the line of sight. Try to find a path that reflects the signal to repeater. Okay, watch this now. What they're saying here is this. Let's say I'm on the other side of downtown LA, and I'm trying to hit a repeater in Palos Verdes. There's a lot of buildings in downtown LA that are going to interfere with my signal getting there. So it says what I can do is I can use the antenna that's got a lot of gain, and let's say that there's Palos Verdes repeater down there, but I got a couple buildings in the way. Well, what's up behind me when I'm in downtown LA? Hollywood Mountain, right? I could take this antenna, believe it or not, and I could point it up towards the Hollywood Mountain, up to the sign, and bounce energy off that hill, and it would bounce back towards Palos Verdes. Okay, that's what they're saying, okay? We're using a directional antenna to access a distant repeater where building and obstructions are blocking the line of sight path, and try finding a path that reflects signals to the repeater. Okay? Another one is, if you live on the backside of Palos Verdes, you can't talk to repeaters up in Hollywood. Sometimes you can't even talk to repeaters on the top of Palos Verdes. So what some cams have done, that live way on back of Palos Verdes, they've got these antennas pointed out to Catalina. They bounce the signal off a catalina, it comes back to the top of the repeater on top of Sal's phrase. So that's what that's all about. Okay? So many times hands need to locate sources of noise interference which are jamming, and so we use what's called direction finding antennas. Sometimes there's people who intentionally put noisy signals into our repeaters. Okay? And so what happens is there's some very smart hams that know how to take antennas like this and go running around in their car, and they can actually find out where that noisy person's radio is coming from. They can go right down and find this house, and then they report them right to the FCC right then. Okay, and that person gets fined. Okay? So we do this using directional antennas. Yep, we have to know what direction's coming from. Some hams engage in hidden transmitter hunts to practice. There's a thing called transmitter hunts or fox hunts, and they practice doing this. Okay? Directional antenna is also used. Is also what is used for hidden transmitter hunts. Okay, fine. Remember this. Again, this is a hobby. People have a little game on the weekend. They'll say, someone will say, "Okay, we got a little transmitter down here in Torrance. See if you can figure out where it is." And people will take their directional antennas and they'll drive around in their cars. The first ones who finds it, they win. This is called transmitter hunts. But these people are also the ones who find the folks who are jamming our repeaters. Oh my God, is that the end of that one? Holy cow, that's wonderful. Okay, all those props for that. I'm racing through this a little. Okay, this one's called Finding Some Coax. Let me move some of these antennas out of the way. Get this one here. Okay, now I've got to get the radio back here. This connector is so hard to get on. Okay, we're going to talk about coax. Now, what is coax? You notice that the thing that goes to these antennas is then these pieces of cables. Okay? So this is coax. We typically, not always, but we typically connect our antennas using a piece of coax. Okay. So, what is a piece of coax? Well, here's a picture. Here's a real one. Okay? So it's a piece of copper in the middle, and there's some insulation here called polyethylene dielectric. And then there's a copper braided shield. Okay? And then there's just a protective outer plastic rubber jacket. Okay? So, coax is a center wire covered by insulation and a metal shield, and it's called unbalanced line. Don't worry about why. Okay? The braided shield is going to be connected to ground, and the actual signal goes through the little center wire. Okay? So, all I want you to know is the black outer jacket is resistance to ultraviolet light, because if ultraviolet light could damage the outer jacket, it would then allow water to enter into the cable. When water enters into this cable, it loses all of its good properties. Okay? So this is to keep ultraviolet light out and to keep all the moisture out of here. Okay? Moisture contamination is the most common failure for this kind of cable. So if you get this cable that's been outside in your antenna for a couple of decades, it could be time to replace it. Okay, it says most common impedance for coax in amateur radio is called 50 ohms. So this is what you just have to memorize. This is called the impedance. Okay, and there's different impedances for different kind of coax. But in amateur radio, we stick with 50 ohms. Cable companies and satellite companies, they use 75 ohms. Just remember the word number 50. Coax is most commonly used to carry RF signals. That's our radio signal between our radio and antenna. Yes, that's where we use it. Coax is the most commonly used type of antenna radio feed line because it's easy to use and requires very little special installation. Good. All we have to do is put a connector on it, plug it right into the back of our radio. Right there. Bingo. That's it. Okay. So you buy coax by the feet, you put the connectors on, and you're done. Sometimes you can actually buy it with the connectors on. Okay, so the coax attaches to our radio or other device using a connector. Well, there's different kind of connectors, but this one here says the PL259. Just remember that one, and that's what these are. And these are very common for the HF frequencies. Okay, but once we get up into the frequencies that you'd be using up in here, the VHF and UHF, they switch to a different kind of connector. You won't see the difference unless you're really close. So just memorize that. Type N is the most commonly used frequencies, about 400. However, you will not see a type N connector in your HT because they're so big. The ones on the HT are nice and small. Well, you don't see any connector. What you see is an antenna plugged right in. You don't see a big connector. Coax connectors exposed to the weather should be sealed against water intrusion to prevent an increase in feed line loss. What's all that mean? Let's say I've got a connector hooked up to my antenna up on the roof. Okay? Hooked up to my antenna up on the roof. How long is it going to take before all the rain gets in here and mucks it up? Not too long. So when I've got a connector on an antenna outside, what I do is I take a piece of tape and I just tape. So the moisture never gets in that connector. Now in the house, I don't have to worry about that. But outside, moisture is a problem. Let's see. Have to do that one. Coax cable is frequency sensitive and inherently has some losses. Okay, I'm going to show you a chart what that means. That means at different frequencies, just because energy comes in one end of the coax doesn't mean it comes out the other end 100%. Different kinds of coax have a certain amount of loss inside. And so I could feed energy or power here, watts. I won't feed all the watts out here. That's what that means. So the amount of signal that actually gets through the cable depending on the frequency of the signal, and I'm going to show you that in a second. There'll be a chart here on the next page. As the frequency of the RF signal increases, as the frequency gets higher and higher like this, the amount of loss in the cable increases. So if I feed energy from this radio through a cable, I'll get a certain amount of watts that come out. But when I feed energy at these frequencies, even if it's the same amount of power, a lot less ever makes it to the antenna. And we'll show you that in a second. Okay? So let's forget this for 1 second. Let's go right to the chart. It's a complicated chart, but I'm going to tell you where to look. Okay? Here's what I want you to look. Start right here. So here's what we've got. We've got a radio. Let's say it's my radio that's on the table here. Puts out 100 watts. And what we're going to do is we're going to have what's called a dummy load. And this is a dummy load. It has a way to absorb the 100 watts. And we're going to take this watt meter, which is this meter right here. We're going to put it all the way down the end of the 100-foot long piece of cable. We're going to see how much of this 100 watts ever makes it to the end. Okay? So here's a standard little cable. It's called RG58. It's small. Here's all you want to know. There's no questions about this. So here's the answers, generally speaking. At 10 megahertz, 67 watts made it. But up here at 400 megahertz, only 4 watts made it. Now we started with 100. So if you had a 100-foot long cable and you start with 5, only 4% of that 5 is ever going to make it through a 100-foot cable like this, which means you wasted your time. Then we can go to some larger cables like this stuff. And let's see, at 10 megahertz, 94 makes it. Oh, that's not too bad. But at 400 megahertz, only 1/3 makes it. So again, you started with 5, you had a 100-foot long piece of cable out to your antenna in your house, only about 1.5 watts are going to make it. Okay? And then some people have this stuff called hardline. It's actually coax, but it's a hardline. And at 10 megahertz, 100 makes it, and up here at 75. So the whole point is this. The larger the cable tends to have less loss. That's the whole point you want to remember. Okay? So the larger RG8, which is the most very common for HamRadio use, has much less loss than the smaller cable, RG8. That's what you want to remember right there. Okay? They have another thing you want to remember. It says air insulated hardline. That would be this stuff here, except it has the air inside here, not this other stuff. Has the least loss at your frequencies, VHF, UHF, and that's not shown above. Another type of coax is called